Chair. My name is Elaine Matos, and I'm the chair of the SEG Women's Network Committee. And I'm here today actually wearing two hats. I'm here as a representative of the SEG Women's Network, and also representing the Geoscientists Without Borders, as I'm also part of the Geoscientists Without Borders Committee. So today we have, in celebration of the International Women's Day, we have organized this webinar that highlights some of the efforts that some of our women geoscientists are leading that contributes to a sustainable society, as well as making a positive impact in communities around the world. As some of you know, the theme for the International Women's Day 2022 given by the United Nations is Gender Equality Today for a Sustainable Tomorrow. And I'm happy to be here and host this event alongside with these two incredible scientists, Dr. Katrin Sieron and Dr. Patricia Persaud, who I will be introducing in a few minutes. Before we go into the website, into the webinar, sorry, I would like just to give a very quick introduction for those of you who are not familiar with the Geoscientists Without Borders program. So what is the Geoscientists Without Borders? Well, this is a program that it's an SEG, an SEG program, and it enables geoscientists to deliver vital humanitarian relief to communities in need around the globe. So the GWB brings capable scientists together with communities coping with environment hardships and natural hazards to solve their problems. How the program works? Well, the program provides funding for these projects, enabling geoscientists to work hand in hand with the local talent, local community, teaching them critical skills to build projects that will have lasting effects for generations to come. The program is aligned with the UN Sustainable Development Goals. I'm not going to go through all the details on the goals. You can have, if you are interested in learning a little bit more around the goals, you can have a look at the UN website. They have a very good detailed descriptions on each one of those goals. And I think one important thing to mention in here is, due to the nature of the GWB program, majority of the projects touches in more than one of those goals. So where are we in terms of projects? So the GWB has funded over 55 projects, and we are still funding, and every year we're looking into more projects to fund. Distributed about in around 34 countries around the world. I will show you in another slide where. We have worked together with more than 670 students, with a partnership with more than 80 universities and 70 community partners. So that's a very, very large program with impact everywhere in the world. And if you are not familiar with the Geoscientists Without Borders program, I do recommend you having a look at our website and seeing the many projects that we have around the world. So on the next slide, I'm just kind of want to show you a list of the projects. You can see the projects that started early in 2009, 2010, and we have been awarding projects every year. But one good point to make is that all of this is done with volunteer work. and through the support of donors and companies that provide grants to so we can fund those projects. And I thought I had an additional slide in here, and I don't, and I apologize. And we would, before we move on, I would like to thank all the donors, the individuals who are sponsoring projects, as well as some of the companies that have been funding and being partners of us from day one, like the Schlumberger, Conoco, and most recently Baker Hughes, who has also helped in the last year or so. So thank you very much. And without further ado, let's move on to our to the webinar. Before we move on to the webinar, I want to kind of give you an introduction on the presenters. So our first speaker is going to be Dr. Patricia Persaud. She is an assistant professor of geophysics at the Louisiana State University. I'm going to stop sharing here so Patricia can share her screen. So going back to Patricia's bio. So Patricia is an assistant professor of geophysics at Louisiana State University. She graduated from the University of Houston with a bachelor's in geophysics and holds a PhD in geophysics from the California Institute of Technology. She was a postdoctoral fellow at the Lamont Doherty Earth Observatory of Columbia University. She is a 2021 fellow of the Radcliffe Institute of Advanced Study at Harvard University and a NSF Career Award recipient. She works on seismic imaging with large N arrays and monitoring the formation at volcanoes and underground salt caverns. Her group also uses deep ocean drilling and oil industry borehole data to constrain stress. And without further ado, I will pass it on to Dr. Persaud so she can carry on with the presentation. Thank you very much, Patricia.
Thank you. Thank you. Can you see my slide? Okay.
Yes, we can.
Okay, perfect. So hello, everyone, and welcome. Thank you, Elaine, and the SEG Women's Network, and also the GWB for organizing this webinar and inviting us to present. So today I will be co-presenting with two brilliant early career scientists who are doing societally relevant research in one of the regions on Earth with the highest seismic hazard and risk. So this is the Alpine Himalayan Belt. First, I will give an overview and an introduction to our GWB project. Then Ritu Ghosh, an LSU PhD student, will discuss some of the technical results from our project in Myanmar. Chiara Nardoni, who is about to start a postdoc at LSU, will then close with a discussion of another important consideration that we must keep in mind in seismic hazard studies. So to start, the photo here shows Pio and Tinzar. These are two students at our partner university, the University of Yangon in Myanmar. The photo was taken just after they had retrieved seismic stations that were installed around the city. And this project would not be possible without their efforts and the efforts of other colleagues in Myanmar. So it's well known that Southeast Asia is one of the regions with the highest seismic hazard in the world. This map depicts the seismic hazard as peak ground acceleration, also called PGA, with a 10% probability of exceedance in 30 years. It shows a high seismic hazard in Myanmar with expected peak ground accelerations of 2 to 4 meters per second. And it provides a clear picture of how devastating the shaking could be if this region was hit by a major earthquake. Myanmar is located in one of the world's most disaster-prone areas with not only frequent earthquakes, but also storms and floods affecting millions of people. Like most of its major cities, Yangon is affected by two major earthquake threats. The city is located just 85 kilometers from the major active Sagan fault, which is similar in length to the famous San Andreas fault and is capable of a magnitude 8 earthquake. In addition, earthquakes as large as magnitude 9 are expected due to the subduction of the India plate. Perhaps what is more critical is Yangon is located, like most major cities in Myanmar, in a sedimentary basin, where the ground shaking gets amplified due to the soft sediments and the basin shape. We were motivated to work in Yangon because the shape and the depth of the sedimentary basin beneath the city is not well known. And this presents a situation where applying some of the geophysical approaches we developed in Southern California can be impactful for Yangon residents. In this animation, showing the basin amplification effect near the San Andreas fault in Southern California, we have simulated ground motions using an earth model that does not accurately represent the basin structure. We can see that there is a triangular shaped wedge around the Salton Sea that has very high amplitudes of ground motion. This is an artifact of the earth model that is being used and shows that meaningful seismic hazard estimates require accurate models of the subsurface to show where and also for how long strong ground shaking will occur. Our GWB project is called the Myanmar University Seismic Experiment, or the MUSE project. We have also targeted the Yangon region for our study because of its high population density. It has a population of over 7 million and is the commercial center of Myanmar. As shown here, the city is densely populated. In line with the theme of promoting sustainability for tomorrow, in 1930, for example, the magnitude 7.3 Bago earthquake occurred just 75 kilometers from the city at a time when Yangon was still small with about 400,000 people. And the earthquake caused the loss of 500 lives. Today, the city has a population that is almost 20 times larger and is ill-equipped to handle another large earthquake. I want to make sure to acknowledge the role that Kin Win, the head of the physics department at the University of Yangon, played in getting the project off the ground. Kin is the third person in the photo from the right. I had reached out to different people in Myanmar and she responded with enthusiasm for the research and the training programs that we had in mind. I visited her university in 2018 and piece by piece, the project started to grow. In 2019, we hosted an international symposium at LSU where Kin, Mio Tant, and So Min from the Myanmar Earthquake Committee visited us to establish collaborations. The MUSE project has three main goals. The first is to organize and lead geophysics training for professors and students from around Myanmar. The second is to establish university programs and local research in geophysics. And third is to determine the basin structure to help improve estimates of ground shaking from a large earthquake. Our project has already had a number of positive impacts. It has helped launch a new geophysics program at the University of Yangon, which is the first in the country. And 18 universities around Myanmar are involved in the project. It is a cross-disciplinary project with participants from computer sciences and physics involved. And it is inspiring a similar effort in Bangladesh that will be led by Ritu Ghosh. Here I'd like to introduce the members of the MUSE group. That's Ritu on the left, Joseph in the middle photo with me, and Kiara on the right. Now we are in March 2020. We have 45 participants from universities around Myanmar who are involved in the project. We also have our equipment shipped and cleared customs in Myanmar. However, due to COVID-19, the US participants were not able to travel to Myanmar to complete the training and installation of the equipment. So we instead trained a group of students and professors from the University of Yangon, and this was done virtually. The group installed and picked up 110 compact seismic instruments called nodes around the city. The next few slides are photos of the pickup of the nodes, which occurred in May to June of 2020. Here I'm showing the different settings where the nodes were placed. Part of our pickup team is shown in the top left photo. The nodes were placed at the sides of the streets, in backyards, and in many instances, right where people live. They were buried beneath a couple of inches of soil, and the homeowners were given a sheet with contact information and details on the project. This type of deployment requires interacting with the public to inform them of the project goals and how it will benefit earthquake hazard research where they live. These are two colleagues from the University of Yangon in front of their geology department cleaning the nodes before they are sent back to the US. The right two photos are locations where the nodes were installed, and the lower one shows the nodes being cleaned on site. The upper one shows that the instruments can be installed almost anywhere because of their compact size, and they do not need to be deeply buried, as is the case for traditional broadband seismic stations. So in summary, our fieldwork had a high success rate despite having to adjust our installation strategies and deal with some logistical hurdles, which are to be expected. No instruments were lost or damaged in the field, which is unusual for any setting anywhere in the world. And all nodes were successfully returned to the US. We had also a 100% recovery of the data. That's it for my part of the presentation, and I'll now turn the virtual floor over to Ritu.
Hello, everyone. My name is Ritu Ghosh, and I'm a PhD student at Louisiana State University. And I am from Bangladesh, which is very close to our study area, and it has the same seismic risk. One of the reasons of my interest in this project is the impact it has raising seismic hazard awareness in those regions. The project also encourages seismic hazard studies in those countries where the scope and the resource is very limited. Next. This is a map of Myanmar and the nearby countries. You can see Bangladesh in the western part of the map. This is where I'm from. And this is also a very densely populated country. And the area you can see in to the west of Myanmar, the Indo-Myanmar range, which is an accretionary wedge formed by the oblique subduction of Indian plate beneath the Burma plate. And this region hosts all the deep earthquakes in that area. On the other hand, earthquakes in Sagaing Fault Zone, which you can see running through the central part of Myanmar, the earthquakes are shallow, close to the Sagaing Fault. Sagaing Fault is a right lateral strike slip fault. The map here is also showing all the major cities of Myanmar. They're marked by the tiny brown boxes. And you can see all the big cities are located in the central basin, and they're very close to the Sagaing Fault. Next. This is our study area in Yangon City, which is the largest city of Myanmar, and it used to be the capital of the country. And Yangon is located 35 kilometers west of Sagaing Fault and in the southern part of the central basin. The first figure here is showing the seismic area in Yangon from our 2020 deployment that was already explained by Dr. Persaud. The brown triangles here represent the nodes that has been installed. Next. So for my study, I'm using receiver functions to identify basin structures. Receiver function is a well-established seismological technique for extracting information from Earth's interior. When P waves travel through the Earth's interior, part of the P wave energy converts to S wave at different velocity discontinuities. And these P to S converted phases can be obtained from receiver functions. This provides some constraints on the depth and velocity contrast of the discontinuities in the subsurface. Receiver function is a deconvolution process which is applied to seismic signals to retrieve near receiver velocity structures. In this slide, figure 1 shows a schematic of conversions that can be produced by a P wave at a boundary, and figure 2 is showing the synthetic receiver function that can be produced from the conversions at figure 1. Next. We need teleseismic earthquakes to compute receiver functions. And the table here is showing the teleseismic earthquakes that were recorded by our stations in Yangon. For receiver function computation, we need teleseismic events with a magnitude greater than 5.9 and an epicentral distance from 30 degrees to 90 degrees. And with the 1 month of deployment, we were able to record 7 earthquakes of that category, and 5 of them produced good receiver functions, which I'm going to show in my next slides. Next. The closely spaced nodes make the interpretation of the structure over small lateral distance possible because the conversions can be more easily traced from one station to the next. The nodal receiver functions have stronger conversion and multiples with larger amplitude after the direct P arrival. The higher frequency content of nodal receiver functions have the ability to reveal the sediment basement interface. For line M2, which is highlighted in the map here, the receiver functions were computed for 7 events for frequencies 1, 2, 3, and 4 Hertz. Meaningful receiver functions were produced from 5 events, and in this slide, I'm showing the receiver function from magnitude 6.1 Philippine earthquake. In the receiver function profile here, the vertical scale represents time, and the horizontal scale represents the stations from east to west along the M2 line. The continuous conversions are visible in the receiver function plots. Detailed analysis from multiple frequency receiver function from different events for all the 3 lines will help us to identify the sediment basement interface and any other important basin structure in this region. Next. So these are showing all the continuous conversions in the receiver function plot. The brown line, the orange line, and green line, they're the different set of interpretations from the receiver function. Next. So a similar project has been carried out in Southern California. The project is named Basin Project, where we deployed 719 nodes along 10 seismic profiles across 3 basins in the northern Los Angeles area. The area is located in the vicinity of San Andreas Fault, which is also a right slip transform fault. The top figure here is showing the seismic area, which are color-coded by deployment years. The goal of this study is to map basin structures underneath this highly seismic risk region. The success of Basin Project inspired the Muse project in Myanmar. Here I'm presenting some examples from the Basin Project as a potential result that will be produced from the Muse dataset. Results were presented in this slide from 61 stations along SB2 line, which is the easternmost yellow line, the north-south trending line, if you can see in the top figure. And in the bottom figure, 3 Hertz receiver functions were presented along SB2, and the brown line is interpreted being the sediment basement interface. The line showing a shallow basin to the north and a deeper basin to the south. Receiver functions are presented in time in the bottom figure, and the middle figure is the time to depth conversion of the sediment basement interface from receiver functions. Results show that the basin along SB2 line has a maximum depth of around 3 kilometers near the Loma Linda Fault, which is close to 10 kilometers along the profile distance. Next. This map here is showing basin depth along the seismic area in the northern Los Angeles basins. The dense nodal seismic array helps to reduce uncertainties in receiver function interpretation due to their high lateral resolution, and a more complex basin structure can be produced from such data set. For an accurate seismic hazard estimation, we need a better understanding of seismic amplification in the basin, and a detailed basin structure is required for that. That was all from my part. I will now turn it over to Kiara. Thank you.
Thank you, Ritu. Hello everyone, I'm Katrin Ardoni. I'm getting my PhD at Roma Tre University in Italy in collaboration with a professor at the JGU University in Germany, and I'm gonna start the postdoc at LSU University this summer. Part of my project will be the application of seismic attenuation tomography to the Southern California areas. So today, I would like to give you an insight about seismic imaging, especially about how seismic attenuation has improved, has become an efficient imaging attribute to improve our knowledge of the propagation medium at very different scales and in combination with velocity tomography. Next. So seismic attenuation imaging can be applied in deformic rocks. When the rocks go through a deformation process, this generates earthquakes, and the rock physics using rock samples reproduces the deformation process in lab and uses attenuation as shown in figure with blue and yellow anomalies. The rock physics uses attenuation to visualize the fractures obtained from the deformation process. This is an example of the application of seismic attenuation imaging at the very small scale. Next. Since decades, most of the attenuation tomography application have been performed in highly heterogeneous areas, such as volcanoes, to visualize the structures of the volcanoes. In fact, attenuation has been added also to the hazard maps. Next. Attenuation imaging can also be applied and has been applied in less heterogeneous areas, such as across faults, fractures, especially when the fluids, gases, turn out to be the main attenuation factor and can induce seismicity. Next. So, attenuation has shown its potential in seismic attenuation, in seismic monitoring, as it can detect fluids and gases accumulation and propagation in the subsurface. This figure shows two attenuation maps related to pre and post sequence data of a seismic sequence occurred in central Italy in 2016 and 2017. We can see that attenuation allows us to detect gases volumes, the dynamics of gases volumes during, before and after a seismic sequence. So this is important. This shows us how attenuation is important also in high seismic hazard region as central Apennines and central Italy is. Next. Moving to a larger scale, we found out that attenuation is sensitive to large scale crossal structures and is able to detect the propagation effects, for example, due to the presence of a crossal waveguide that causes waves reverberation. So so far we have understood how important, how attenuation is important and allows us to get more information in combination with attenuation tomography. But taking a step forward, so next. the application of a full waveform forward modeling, both at local and regional scale, allows us to answer the issues related to the structures we need, and we need to visualize and understand, especially in high seismic hazard regions where amplification or reverberations could happen. Next. Thank you for your attention, and if you have questions or comments or just curiosity, feel free to ask. Thank you. And yeah, I think I can leave the stage to Katrin.
Thank you, Chiara, and thank you, Patricia and Ritu, for your presentation. Those are very interesting results, very interesting project. We are very happy to see you here. Just for taking into consideration the time, what I'm going to suggest is that we take all the Q&A after Dr. Sieron presents. So for those of you who have questions, please feel free to stop typing in your questions on the Q&A part of the chat, and we will be taking your questions after Dr. Sieron's presentation. While you get your presentation up, Katrin, I will give you a brief introduction on Katrin's background. So just bear with me for just 1 second, and then I will hand it over to Katrin. Okay, so Dr. Katrin Sieron has a master's degree in geology and a PhD in volcanology, and she's been trained in Germany, Canada, and Mexico. She holds a permanent research position at the Center of Earth Sciences at the Veracruz University in Mexico. She has published in several indexed and dissemination journals, apart from numerous technical reports and outreach-related works. She has been a member to Mexican National System of Researchers, SNI, since 2014, and participated in multiple national and international research projects, of which she led 3 of them. She is a member of the Seismological and Volcanological Observatory of Veracruz, Mexico, and has presented her work in more than 20 international conferences. And with that, I will pass it on to Dr. Sieron so she can present her project. Thank you very much.
Many thanks for the introduction and also for the chance to present the work over here in this nice event. I'm really grateful to be here, and also to the GWB program. I just want to talk about a project that was on one of the highest mountains in North America. That's actually an active stratovolcano. It's called Pico de Orizaba, or native language Mountain of the Star, Citlaltépetl. And just want to talk about what we achieved and what the challenges were during the project, apart from COVID though. So, not moving. Okay, working now, that's good. So where are we? On the right-hand side, you can see Mexico with the Trans-Mexican Volcanic Belt. So in Mexico, you have a lot of active volcanism in a broad zone stretching from east to west across the country. And actually right now, there's 2 volcanoes that achieve a lot of attention. That's Popocatépetl and Colima volcanoes. And they achieve a lot of attention because they're actually in eruptive phases right now. But there's many volcanoes, as Pico de Orizaba volcano, that are potentially active and but are under monitored. What does that mean? Sometimes they just have one or no seismic station to monitor, so people are just not prepared when they reawaken. This had been experienced during the 1981 eruption of Chichon volcano, and in a really sad way. So what's the particular context of this volcano? It's not only the highest in Mexico and the third highest in North America, but it's also, it has a really steep, if you look at this picture at the lower part, you can see that Pico de Orizaba with over 5,600 meters above sea level, and then it goes the profile down to the ocean to 0 meters. So you can imagine the potential it has. Just any kind of flow that's deriving from the volcano has an extraordinary potential just because of its potential energy. So many times people forget about the hazards related to volcanoes when they're not erupting. Volcanoes, just compared to a human life, are so old that people, most of the times, they're just talking about mountains, not volcanoes, and they're not really conscious. So, and especially when it's not smoking, when there's nothing coming out of it, people really underestimate. So there is always, it always has to be, has been my, one of my greatest interests to get some attention to mitigate, to prevent hazards and tragedy related to all kind of phenomena. But specifically, I'm interested in studying phenomena that are related to a volcano that's not erupting right now. For example, the lahars that are gravity-driven mud and debris flows that can occur every time when you have some kind of water source and some kind of sediment source. So when you look at the pictures, you can see that the vegetation line is about at like 4,000 meters above sea level, but the mountain is over 5,600 meters high. So you can imagine that there's a lot of area, there is no vegetation, it is highly unstable, and then just add a little glacier to it or a strong rainfall during, for example, hurricane crossing. So you get a potential disaster. Most of the times it's hard to get financiation, especially when you want to study a volcano that's not active right now. So I was really happy to be able to do something about the situation with the help of this project. When you look at it, here I have some pictures from the higher part, from the upper part of the volcano. You can actually see the glacier, that's the last one in Mexico. The other ones have disappeared already. And you can see the highly unstable slopes, the upper slopes that are affected by erosion, by the glaciation of former times, and also the water that's coming off. I don't know if you can actually see it in this picture, the water that's coming off the glacier, and also the hydrothermalism that's due to the volcanic activity. So this is highly unstable. And then by the driven by the retreat of the glacier, you get exposure of these affected rocks. And it's actually quite awful just imagining the amount of material that's lying just there, just waiting to be put in motion by some source of water. So what I would like to mention is that it's all about magnitude. So you can get, just as indicated in the hazard maps, you can get scenarios that are like high volume, high magnitude that reach far away. For example, during Pico de Orizaba's history, that's a little dot right here, it has experienced collapses of its edifice due to hydrothermal alteration and just becoming unstable, sorry. And then this material moved up to the coast. It's like 70 kilometers from the summit. So this would be kind of worst scenario. But then you get others that occur every rainy season, and especially when hurricanes are crossing, and you get the minor events. The minor events are affecting people that are living on the slopes, and in every rainy season, and they kind of adapted to it and got used to it. But it's all about magnitudes, as I said. So when something bigger is happening, nobody is going to be prepared. Over here, I just put some little Google Earth image of one of the villages that is one of the first ones being hit by a potential lahar. So you can see the river right going through the village. And actually, during the studies of this project, we also found out that people, because of inheritance, are moving more and more towards the river system. And if you imagine, this first village is about, well, the lahar would take maybe 10 minutes, 15 minutes to reach this village. So it's many kilometers away, but still it would be, so this gives us the chance to actually alert them before the lahar is getting there, if we can detect it on the high slopes where it's forming. So this is the main goal of this project. Also, just side information, as I said, there is a high level of instability in this mountain. Over here, you can see another side. There have been really big rock falls of many tons of material going down. And you can actually see the rugged surface, and you can imagine what's going on there, even when it's not active. Just putting the attention towards lahars and major rock falls. So what did we do during the project? We did some geophysics to get a notion about the material that's there, unconsolidated material that's laying there, the water source, just measuring rainfall and estimating the volume that's still left there when looking at the glacier. We did geology work, just studying the former lahar events that have happened. We did some cartography because there's not a good model being available for this region. So with high precision drone-derived dams, we could help. And then we started modeling the lahars and rockfalls that would happen on the basis of all the parameters acquired of the geophysical and geological studies. And we built a monitoring system of the conditions that can trigger these events. That's seismic events and extraordinary rain events. So just a little bit about the challenges. I think many times it's quite difficult to access these high altitude regions, and even worse to do geophysics there. You have to imagine just pulling the equipment like above 5,000 meters above sea level is just, it's just, to say the right word, crazy, because it's hard to breathe, it's hard to work, and you really need like people that are kind of prepared to work on like under these conditions. And I'm really happy to have found those people that have that same interest, even students, and that had the conditions and the interest to participate in the study. Over here is just some figures of the results we got by the radar. That's the radar, what you can see there, that we pulled over the ice of the glacier. And so we could get a thickness, which was then estimated to get the thickness of the rest of the glacier body. Then also another challenge to fly a drone, like over, I don't know, 4,000 meters above sea level is really a challenge. And not also because of the altitude, but also the big steep valleys you have to fly into. So this was also a big challenge. But it was worth it. We got high resolution images of the whole gorge that's draining the glacier and where a lot of the unstable material is located. We got also thicknesses of the sediments that are unconsolidated and lying there. So we can get an idea of the volume to be removed by potential lahar vents. We also were able during the project to build infrastructure that kind of protects the equipment that we acquired. What kind of equipment? We have Raspberry sensors. We have also different kinds of meteorological stations, Davis and Campbell, for measuring the rain at these extreme altitudes. And we also have cameras that are looking at the gorge at a high level, like above 3,800 meters above sea level, just to detect the lahar and like early on, like in the proximal area, and to be able to alert people that living downslope. We also included some vulnerability studies. That's really a specific kind of population that you have there. You have to imagine they live in really vulnerable situations, like just looking at education, looking at the building, the housings, and also they really depend on the volcano. They live off everything that it has to offer, like the wood, forestry, and also farming and stuff. And then another part that was really important is outreach, not only being there and living with the people in the field and talking to them, but also we did little festivals for the kids. We not only publications in research journals, but also like in native language in Spanish and in local little newspapers so that everyone would get it. Over here, you can see, again, imagine to construct anything above 3,500 meters above sea level. It was a really big challenge. Just imagine pulling up all the, carrying up all the materials. You can use a car, but only like a few kilometers near the point where the stations had to be built. So just imagine the carrying up like all the rocks, the stones, the cement and everything. We had to use horses and local people that could stand the effects of the altitude. So it was really a big challenge, and I'm really happy to have found so many people that were helping during the way. So what did we do? We actually installed at the gorge that it's draining the glacier, as I said, to the north side of the volcano. We built several stations there that protect equipment, the meteorological stations and seismic stations. And we concentrated all the signals and the data of the different stations at one point and are transmitting this 70 kilometers to our research center and observatory. We're receiving the signals and the data and can analyze it to determine thresholds of rainfall, for example, that's critical for triggering lahars, and also get the signals of rockfalls, etc., firsthand. So just to show from nothing there, we built first the meteorological stations and then the huts that are protecting it. I'm just showing two of the sites. And you can also see, for example, at this picture, you are at 4,000 meters above sea level, and you can see that the biggest part of the mountain where the lahars are forming is still up slope. And over here, another station that we built that has a camera actually to look at the gorge to see the lahar coming, detected also by, well, because of the seismic signal, we have a raspberry shake there also. And then it all gets transmitted to our main station and from there to Jalapa City, where the university and observatory is. So this gives you an idea what we constructed during this time. And really crucial is the precipitation monitoring. Why? Because, well, it's one of the main triggers, because as I said, the material that's unconsolidated there and that's lying around there is a lot. But actually the limiting factor for volume, for the final volume of the lahar, would be the water. So this is crucial. We have to get an idea of what happens during a hurricane, what happens during an extraordinary rain event, a normal rainy season, and what again gives us the crucial amount of water to trigger a lahar. So I think it's also, at least in Mexico, there's only one other spot I know of where this high mountain rain monitoring is happening. What is really interesting during this time, or what was really interesting during the time of the project, is we were actually living with the people on slope. So we were not staying in hotels like normally would happen. We stayed there at the site at 3,000 or 3,200 and 3,400 meters above sea level, not only because of acclimatization purposes, but also to get in touch with people, talk to people, see how they live, and just present our project directly, locally. And I think again, I'm really grateful to all those people that were providing housing and everything to us and all the students that participated. And it really gave us a totally different view than the one we have like just sitting in the office and in a research center. So I think this was actually crucial and is crucial to make this sustainable. So yeah, just to present some of the results, we were really happy that the system were working, because you have to imagine the climate situation and the altitude, and it's just, yeah, for us, it's incredible that the instruments are working. And so what did we achieve? Well, we got precise channel geometry and could analyze all the parameters that make that trigger lahars, not only the glacier thickness and potential volume of sediment and ice up there, but also we could estimate the precipitation amounts during the rainy and the dry season. We could look at the channel geology, and together with the high precision drone images, we could estimate susceptibility along the channel. And we also have a first really high altitude monitoring system for precipitation. We have a telemetry system. We are using radio signals to get the signal to our observatory and research center in real time. And we are also really proud of having trained many students from different areas that participated actively in the projects. And we have a lot of data to work with for the next years, and hopefully to help understand these systems better. This is just one of the social studies of this first village that's going to be hit on the northern flank, just the northern flank where the glacier is situated. And you can see like more or less the conditions that people are living in. And you can see this potentially awful situation as the many villages are being constructed close to the river system. And as I said, there's also a high tolerance level of the people that are living there, because they're used to the smaller events. They're just used to it. They even have, they're just advising each other and watching over the river, for example, when a lot of rain is falling down, but they're just not aware that this could increase, the volume could be a totally different one, and then nothing would help. So this is just to show where we got the students from which careers and what they did in the project during the 2 years. We also, same as the other project, we would have liked to involve more students and have more students, for example, from the US coming over, but it was not possible because of COVID. But in Mexico, we had involved 3 different universities and students coming from 3 different universities and all different kind of areas, like, for example, geophysics, social studies, climate change, but also instrumentation students that helped up building up the telemetry system, water chemistry and isotopes, geomorphology, and also the hazard assessment as such. So we are really proud of that, because especially early career students, bachelor students were involved, and we really hope to have made a difference. How are we going to do, well, to achieve sustainability? The problem is always the same. When you get a research project, you can acquire infrastructure, but then it's difficult to maintain. So that's why we had the idea, and normally it gets removed, no? After, for example, the duration of a research project, 1 or 2 years, the equipment gets removed. So in our case, we just included the infrastructure into the idea of the observatory. So it's going to be maintained there. And we also have a lot of agreements with different institutions that are willing to help us when we have problems with the functionality of the equipment. We need some replacement or getting up there and just maintain give maintenance to to the huts, etc. So that's our strategy, to just to have it as part of the observatory, and elaborating agreements with the different institutions that are also interested. And we are also sharing the data. We are sharing the data with the National Center of Disaster Prevention and also the Seismological Survey. So this also spreads the interest in this monitoring system and will guarantee the maintenance. That's what I mentioned before. We are putting the effort into the observatory. Also at the observatory webpage, we have all the information on the project, on the GWB project, and people can contact us there. And we also would like for the future, not only seeking the maintenance of the system we built, but also helping understanding the situation in the high mountain environments. But also we would like to improve our data management, because we're just starting with the analysis, and we have there some support from other institutions and other academic people, researchers that are helping us to install, to apply, for example, artificial intelligence system to detect events earlier, and build on our system to improve everything. And last but not least, I really want to thank all of these institutions. First of all, UTSA, like my co-PI, Blake Weisling, was really cool working with you. I really appreciated it. The geophysics department from the Boab University and all the others that are mentioned there. Also the National Park of Pico de Orizaba that helped us getting everything, like the permits to install stuff. And last but not least, the local people that were so helpful throughout the process. So thanks to you all, and thanks for your attention. Also, if you have any kind of questions, I will be here.
Okay, thank you, everybody. This was, and thank you, Katrin. That was another excellent presentation. So we are now open for Q&A. As I mentioned before, if you have a question, please send your questions in. I do see one question here, and it's around, it's more of a general question, and it's asking all of you, what has motivated you to start working on a humanitarian project out of all sorts of projects that you could be doing? Who would like to take that and start the discussion?
I can maybe give an initial response. So I think the biggest motivation is how little is known in Myanmar about the subsurface, and without a better knowledge of the subsurface. And this is really just a seismic velocity model, what we call an Earth model. So without a model of the Earth, it's really difficult to get a good estimate of the ground shaking. And I think that was one of the things, but also being there on the ground. I was in Myanmar before the GWB project was started. And being there on the ground and seeing the interest of local participants and the people in Myanmar, how interested they were in better understanding the geophysical problem that they live in that region. And I think that was one of the biggest motivating factors for starting that project there. And a third component, which I think has to do with the fact that I work a lot in Southern California, and I see how many advances we were able to make there in terms of earthquake hazard and getting a better estimate. And I think applying some of what we already know is just really an exciting opportunity as well. So, yeah.
Thank you. Katrin.
Yeah, me too. I really have to say that I'm really passionate about volcanoes and volcanology. I always have been, but particularly the hazard assessment has drawn my attention like from the beginning for my PhD. So when you are doing hazard assessment, and this is like most important aspect of hazard assessment, is that it is supposed to be to protect people, and especially in vulnerable situations. So I really appreciate that there is organizations and efforts to help people to achieve this, to achieve actually building up systems that are there for protecting people in vulnerable situations. So it's for me, it really has been a pleasure, and I really hope that this system stays for a long time and gives and is going to be the start for awareness that hazards are there all the time, also when the volcano is not erupting in the current moment. And it's so much better to be prepared before it happens, not wait until it happens and then instrument, but before. So I think this was really an awesome experience. And again, many thanks to make it possible, because especially in Mexico, like in the province universities and the local universities, it's really hard to get when you don't get financiation by external projects. You're hardly able to build up anything. So I'm really thankful.
It's good, thank you. We do have a question that it kind of touches upon what you've just said, Katrin, around what the pleasure of doing such work. Someone is asking, what's your favorite experience since joining the program? And I think it's a general question, so it's for whoever wants to take it.
I guess I can say something to that. And this, I guess the question is also since starting this particular project, the GWB project. Yes.
Yeah.
My favorite experience, I think, is just being able, and I think Katrin also touched on this, just being able to do the project, because to do research we need funding. And sometimes it is challenging to get funding to do humanitarian research. Especially I think in geophysics and in seismology for sure. So I think just being able to reach out and get people involved and do the project that would normally probably not happen that easily. I think that was really something that was a very positive experience, because when you work in communities where there isn't an established way, let's say, of like, doing research, the type of research that we do, and you can't just like, leverage those resources, it is a bit challenging to get something started. So I think that experience was really good for me. Katrin?
Yeah, maybe for me, it was the multidisciplinary aspect. I think I am starting to feel the necessity of these multidisciplinary projects, because this really gets you to a different understanding. For example, I'm a geologist, like for my formation, and then started with volcanology, and I work together with geophysicists. I work together with geographers, biologists, and social scientists. So this gives you like a totally different, it gives you a different level of understanding, because it's a system and you have to understand it like from different points of view. So I really appreciated being surrounded by so many people from different areas and being able to discuss things with them, including students, because they are scientists in the making, and it's also really refreshing discussing with them. So I think that's the part part one I really enjoyed, the multidisciplinarity. And the second part would be, as I mentioned before, just experiencing things by being there. That's really, we stayed, for example, at the first plans, we were thinking of spending the money in a different way. And at the end, we spent most of it in the field, because it is so different just being there on site and being there with the people, working with the people, and really sensing and experiencing the system with all its aspects. And it really gave a totally different view on things for me. And these are the two things I really appreciated and enjoyed most. Apart from Stina, you go. Really.
Excellent. The next question I have in here from someone else from the audience as well. It has two parts. One of them is a compliment. We always start with the question. So the person is asking, as a woman, how did you cope being a field geologist in such a harsh condition? And they say that she says that she actually really admire your resilience. So I think that probably goes to both of you, but let's start with Katrin.
Yeah. Well, it's especially, well, I don't know. I think women, well, first of all, I have to say that I was surrounded by people, by men that were really supportive. And I totally enjoyed that part. And I hope that all of you that are out there, being women in science, especially in geosciences, experience that, because it's so helpful. It has not always been that way. But I have the fortune to work with people, with men that are supportive and that are, that's why I think one seeks the right people for doing such a challenging project, because if you do not have the right team, it wouldn't be possible. It just wouldn't be possible. And like, that's why I also have to say thanks to all the people that collaborated, because they made it possible. And the physical challenges, well, we were working on the volcano like before the project, and we chose people carefully. I was myself working in a previous project on the mountain, and I got used to altitude. But we also chose like certain students and co-workers that had some mountain experience, because if not, you're facing the possibility that you won't be able to finish it. So for example, this person that you saw on the glacier pulling the radar was my PI, Blake Weisling, that has like mountain experience for over 20 years on this mountain, and a student that turned out particularly resistant. So he actually didn't show any signs of getting tired or anything, so we chose him. And and also the people from the geophysics students from the Boab University, they didn't show any signs of mountain illness or anything. So we were really like testing people and ourselves and going up slowly, like further doing this, first doing the studies in the lower parts and then the higher parts, and also like getting to know ourselves and our own abilities. No, for example, I did not pull the radar on the glacier, but I was able to be there and look at the geology, for example. So yeah, but yeah, it was really a great team effort, and people are really resistant, the ones I know. So yeah, I'm so happy that nothing happened and that everybody coped with this particular situation. Yeah.
Oh, thank you. That's impressive. Patricia, would you like to add anything?
Yes. So I when I was first in Myanmar, we spent roughly a month in the field, so doing field work to install. And this was a different project. This was to install broadband stations, which it takes much more effort to install broadband stations than to install the ones that we use in the GWB project. And I think it's important to note that there are still parts of the world and communities where it is not normal or it is not common for women to do field work. And it's actually sometimes frowned upon when that occurs. And I think more can be done in those communities and also everywhere in general to make sure that women have those opportunities. There are some women in geophysics and in seismology, for example, who in their own country could not potentially have access to do field work. So I think that is something that I want to highlight, because it happens sometimes that we have graduates from other parts, international female students who graduate, but in their own country, they couldn't do field work. And I think that is an important change that can be improved going forward. And Ritu, for example, is from Bangladesh, and I'm curious to know what her thoughts are on this.
Please, Ritu, now you're unmuted.
Yeah. So, so I did my bachelor in Bangladesh, and in our undergrad program, we go to 4 fieldworks. And in the geology program, the female, we were 20% female in the undergrad program. And when I talk about deployment of seismic stations in the remote areas, which is close to the Indo-Myanmar range in the eastern part, that's the hilly region in the remote. And the scope is, I would say the overall scope is limited, but for women, it's kind of limited, I would say, in Bangladesh or in those areas. But yes, of course, as Katrin said, like when I went to fieldworks, I have had my fellow classmates or with whom I went to work, they were extremely supportive. And right now, I see female students are getting more involved in those kind of studies and going to, field work. So, yeah.
That's good. Thank you. Another question we have is, and this is specific to Patricia. Patricia, what was the earthquake hazard in Myanmar?
Yes, so there are two aspects to the earthquake hazard in Myanmar. So the map that I showed, where you saw that it was red everywhere in the region, shows very high peak ground accelerations expected for those areas. There are 2 imposing earthquake threats there. First, from the Sagan Fault, which is essentially like a San Andreas Fault going straight through the country from north to south. And we expect to have a magnitude 8 earthquake on that fault. But there's also a subduction zone just over to the west, like Ritu mentioned, that is locked and loaded. So in other words, building up stress, and an even larger earthquake is expected from that subduction zone, potentially a magnitude 9. So the seismic hazard is high. It's one of the highest seismic hazard regions in the world.
Okay, thank you. I do have one question, and that's from my side in here. I see specifically in Patricia, and I believe Katrin as well. You've been working on this project throughout the COVID-19 pandemic, right? So my question to you is, how has the pandemic affected your work? And did you see, I think in general, we see a lot of downside on the pandemic, but there has been some positives in terms of communication, of people being able to use the communication tools that we have available today more effectively. So what is your experience working on your projects throughout COVID-19 pandemic? How has it affected both of your projects?
Okay, I'll go first. So I think besides COVID-19 and the impacts of COVID-19, because we work in Myanmar, and so the military in Myanmar seized power again. And right now, there's not a lot of communication with our colleagues in Myanmar. So that is not because of COVID-19, that's because of the circumstances. And, zones or areas that are in conflict, I think it's a difficult situation for everyone, including the scientists there on the ground. So that has not moved us rapidly forward. However, I think in general, COVID-19 and being able to communicate and do these types of like what we're doing right now, I think that has had a very positive impact on the way that we share our research, the communities we are able to reach. And I just welcome that positive aspect, and hope that that also goes on beyond the pandemic period. And I think that being able to reach communities, like share our research, is very important. That scientific communication is something that we often put last, and it's nice to see that be so common in the Zoom world.
Katrin?
Yeah, I can relate to some things there. Well, for me, first of all, I really have to admit, if I wouldn't have been granted the 1-year extension by SEG, GWB program, I wouldn't have been able to finish. That's first thing, because of the pandemic. And for us, it was particularly difficult because it affected, there's like some bureaucracy issues at the universities, especially when you want to acquire equipment. And we almost lost an entire year because of that, because people, well, during the pandemic, there was times when the university was just not running. There were no administrative people, nobody. So this was really hindering the acquisition processes. This was really affecting us a lot. Then also because it was difficult during pandemic to do field work, we got affected by that, but especially the students. Like they all started with us and they had their thesis projects there, and then the pandemic kicked in, and some people already had the data, others didn't. So we had to adapt everything. And also it was quite harsh because students were also helping with carrying stuff and building stuff. So we had to do lots of the field work at the end of the project just by just the researchers and the technicians. So it was additional workload because of that situation. But positive aspects, I think, yeah, well, it's hard to see the positive.
Any positive.
Yeah, because it even prevented the people from the States to come over, the students from the States. So we couldn't involve them at all. Okay. So this was so sad. But the positive aspects maybe is that you learn how to cope with such situations and get things done. It makes you stronger, I guess, and it lets you seek like alternatives. That's maybe a positive aspect. And as you said, the last thing I can relate, yeah, you get used to the sharing information in different ways. For example, we were able to build on the website and stuff. So yeah, maybe in this sense. Okay. And less teaching, I guess you have more time for research. So yeah, this would be another aspect maybe. But yeah, overall it was quite negative.
Okay, well, thank you. It's excellent. We're getting several questions here on the Q&As. So this is a very good question, so I'll read it to you. Did you experience any hesitation or resistance from the local communities while you were doing your research? And if so, how did you overcome this resistance? Patricia?
So yes, I can answer directly and say no, there was not resistance to doing the research. In Myanmar, the people live with earthquakes. They occur quite frequently, large earthquakes, like a magnitude 5 earthquake. It's quite common. And they are also curious and interested in understanding the hazard. So there was no resistance that we experienced, and actually we were helped. And our particular project, as it turns out, it wasn't planned that way, but it ended up being that way. That all of the data that was collected by local people as a result of the pandemic. So I think it shows really huge support and huge collaboration there.
Okay, Katrin, would you like to add something?
Yeah, I'm actually, in Mexico, it's difficult sometimes in the field. On this particular volcano, there's actually communities that are really, like, the entire community is really supportive. And there's others that just want to be left alone. So they would just want to be respected and left alone. So we kind of had to adapt to that situation. But in general, just being there again was the right thing to do, because then you can overcome eventual problems, no? Because you can tell them what you really want, that you're not interested in stealing anything or preventing them from doing their work, that you just can be there and convince them that you want the right thing, that you want to protect, that you want to do something good. So I think sometimes this is just achieved with time, and that's why it was so crucial to stay there and not far away and just go there, do the work and go back. I think that was really crucial in this sense. And I was really overwhelmed by, when we then got known and by the local people, I was really overwhelmed by their way of seeing things, helping us, and resistance, like in this environment, everything. I was really like blown away by that. So but definitely you need some time. In these environments, you need time and presence. And that's also something I would like to maintain, even if the project has ended. Sometimes just go there, give maintenance to the stations, but also keep on talking and keeping the contact with the people, so that we don't lose what we got, like confidence wise.
That's a very good comment. Yeah. There is, and it might be the last question here. No, there's another one. So one question is coming back again to Patricia around the earthquakes hazard in the region. So this question is, was the earthquake hazard in the North region where the 2004 earthquake occurred? And if not, could Professor Persaud touch on the topic again?
Yes. So the earthquake hazard that the previous question, the earthquake hazard in Myanmar, that region is to the north of where the 2004 Indian Ocean, so the earthquake was not in the Indian Ocean, but it caused the Indian Ocean tsunami, right? So it is to the north of that, the Sumatra Andaman subduction zone, and the earthquake hazard is high there. So it's along the Sagan fault. I think that's coming from a student, that question. Yeah.
It could be.
Yes. Did that answer your question?
Let's see if we have make a comment. Okay, we will wait, but thank you for your answer. Yes, it did.
Okay, Alejandro. Thank you too.
Yeah, another question here, probably from students as well. How can you advise undergraduates or postgrads looking for opportunities to get involved in GWB humanitarian geoscience work? So I will take it from the GWB part, and then I'll pass it on to Patricia and Katrin in case they want to add something. So I think there is nothing preventing specifically postgrads and even undergrads in submitting their own projects themselves to the GWB. The only thing you will need is to there are very specific guidelines to follow on what you need to do in terms of submitting your information when requesting a project. But the main thing is finding a project, a good cause that you believe that geoscience somehow will have an impact in solving that humanitarian problem. Finding a good advisor, of course, you need to have a technical group that can support your project, and then submit the project to GWB. We have a committee of scientists who will who reviews those projects twice or 3 times a year when the registration is up. And we are more than happy to receive any type of work. So we have seen projects before that are submitted by students, so there's nothing preventing students from submitting. But on the other side, of course, you have, if you're on the university, you probably have an advisor out there that you would like to reach out before and to make your submission stronger. But I'll pass it on to Patricia and Katrin from their own experience.
Yes, so I have students involved in my project at all levels, and also Chiara is a postdoc. And she's involved in the project. So if there's I think if there's a GWB project that maybe you came across in passing and you're like, that's interesting, or it's in a region I'm interested in, I think it's okay to reach out to the PI or to contact GWB and ask, can you get information on the project? Can you give them your name and contact information to see if you can be involved in the project? Because there's nothing really stopping a PI from involving a student who is not in the project from the very beginning. And once there's funding to support that student, most PIs, I think, would be interested in getting more students involved. And sometimes different programs also have funding available that a student can seek to participate in a project. It doesn't necessarily have to be just GWB funding. And I think students can just find and get that funding and then contact the PI as well. In general, most PIs are happy to have more students and early career participants in their projects. So I think it's a matter of reaching out and making those connections and figuring out where the projects are, which is on the web page, right? There's project information on the web pages, and then contacting the PI because the information is there as well.
Like to add anything, Katrin?
Yeah, well, maybe just in general, I think that students, when they're interested in research in general, like starting from the beginning, from bachelor, master students, if they're interested in research, I think it's the best to participate in research projects. And for example, I myself give each student a chance to choose. Sometimes they know what they want, sometimes they do not. But you can just give them a chance to choose their own project within the project. Like you do a thesis project, and within a larger project, you can do your own research under like a bigger umbrella. And I think this is the best opportunity to get into research in general. And with the other stuff, I would just agree what Patricia said, that whoever gets in, like all of the PIs that get like an email from an interested student, I think, yeah, we're always like passionate about those things. And if somebody else is, I think normally every one of us would appreciate to work with interested student. I totally agree on that.
Excellent. And I have one. Let's see if there's another question came in yet. And no, so I have one last question to both of you. I think one thing that it's very interesting on all the GWB projects is, and I believe it was Katrin that actually touched upon it, is the fact that it goes beyond the geoscience part of the project and involves a huge amount of people with different expertise and different backgrounds and different types of soft skills as well. And I would like to hear from you, what was your experience with those type of interactions? What have you learned from those projects? And what do you see as, what has it changed in your way, if it any? Has it what type of impact has it had on your career going forward? That experience that you take from working with those different background of people and different skills. Patricia?
Yeah. So I think the people that I work with in my GWB project, they have a very different everyday environment than I do. A completely different everyday environment in terms of access to resources and also the bureaucracy and the administrative issues that they have to deal with. And I think knowing that, knowing that your situation is maybe quite different than somebody else's situation really allows you to think more broadly in the way that you do work and to be somewhat more patient and considerate of the situations of others. So I think just being aware that, we are all interested in doing science and moving our science forward and having also amazing broader impacts for our projects. But the situations can vary so much and be so widely different from one country to the next, or even within a country itself. And I think that has broadened my perspective even more to help me think more of how to work with international communities and how to do field work in those settings and things to keep in mind when working in those communities. Yeah.
Katrin?
Yeah, as you said, I mentioned it before. I think one has an evolution of it, like being a researcher, one experiences evolution as well. So for example, for myself, the last two projects I had were of this character, like interdisciplinary, multidisciplinary projects. And I totally love that. I really have to say that. I'm passionate about volcanoes, but I'm even more passionate about interdisciplinary research. And this comes after multidisciplinary research. So if you're open-minded and you actually listen to a geophysicist, a statistical person, a paleomagnetist, a biologist, and you really listen to them, and you really try to understand what they're doing with your limited knowledge, because there's always technical knowledge you need, but you can try to actually understand. And if you do that, you get to this higher level, because interdisciplinary is more than each science by itself. And I think this is what I want to achieve. I'm really sure about this, because the last two projects actually have given me more impulse towards that goal, because I feel that a different kind of understanding is possible when you build on not only your own knowledge and expertise, but on the others' expertise. And I'm totally fascinated by it. It started with a project before the GWB, but at the GWB it was, we really had to fuse things, like to do a real fusion. Like, for example, as I'm a geologist, and this is basically a geophysical project, I really had to collaborate on an intense level with the other co-PI, that's a geophysicist. So we really had to understand each other, discuss, and see, get to this level. So I totally enjoy that, and I totally think it's part of my personal evolution, and I will keep on doing that, interdisciplinary work and multidisciplinary teams. I totally, love everything about it.
Thank you, Patricia, and thank you, Katrin. I think that was the last question of our session today. I want to thank you everybody for attending this session, for the presenters, for presenting your work. It's really, really good to see the those projects that you have presented to us, all the efforts that you have put in the last couple of years or so in those humanitarian projects. Being able to touch somebody else's life with science, I think it's priceless. And I do appreciate your time in being here today. And the time of the audience as well. It was a pleasure having you here. And before everybody leaves, I just want to remind you that tomorrow, continuing the celebration of the International Women's Day, we are hosting a panel discussion with leaders in the industry, 3 leaders that are leading sustainability projects worldwide. So I really ask you to go to our LinkedIn page, register yourself in case you haven't done so, because it's going to be another very interesting discussion from a completely different point of view. Thank you, everybody, and have a great day, and happy International Women's Day to everyone.
Yeah.